So let me briefly recap ISAM for those of you that would like me to do it. Okay? Does this slide look familiar to anyone? Put a thumbs up if you've seen the slide before. Okay. Basically, last lecture, what we covered was you'd essentially have your data files, and instead of using just a sorted file and doing binary search on it, we decided let's build a wrapper on top of the file, an index. And that index would be useful for us navigating to wherever we wanted to go to in the file based on a certain key. Okay? And this is what it essentially looked like. We decided that we're going to have something that, it's built on top of the file, which is this bottom level here, and it will basically be used for navigation. One way of thinking of it is when you've got your index, this is like a GPS. Okay? The GPS is useful because it tells you if you have a value, if you have a value and it's if you're looking for, let's say, 5 or 4, you look at the root node, it's 7. Okay, so 4 is less than 7, so you're going to go to the left. Okay, now you get to the node with 3 and 5. So you scan these values and you say, okay, where do I go from here? Well, 4 greater than 3, less than 5. You're going to go to the value, to the pointer indicated from the middle. It's right of 3, left of 5. You'll go to the data page and you'll search for your value there. That's how navigation works with ISAM. And remember what we said was, sometimes you'll end up in a bit of a spot because you might have this thing called overflow pages. You might have too many values to fit on a page. So what do you do? Well, we just said let's just add an overflow page for now. Right? We just said let's just tack on a value to the very end of the page, or rather just tack on another page actually, and kind of like form like a chain of pages. So here you can see 12 doesn't fit on the page with 9, 10, 11, but it's greater than 9. So what are we going to do? We'll just tack on an extra page with 12, and we'll, just move on from there. And then any value, let's say I insert 13, well, I'll just go over there and insert 13 onto the page that had 12. It's that concept of overflow. If this sounds dumb to you, don't worry, it sounded dumb to the people that invented it too. And that's why we have something better. But before I go on, I just want to check, do people understand how to navigate through a tree? That's the important part. Okay. Okay, so let's introduce something called the B+ tree. So the B+ tree is similar to ISAM. You have your same interior node structure, okay, and you have the same search routine. Less than, you go to the left, greater than or equal to, you go to the right. Okay? But there's a couple advantages here. It's always going to be balanced, and it supports very efficient insertion and deletion. And it's going to grow at the root, not at the leaves. ISAM had this problem where the overflow pages would mean the tree just kind of grows unwieldily large and just starts to, spiral off into this chain at the edge, right? Because you have overflow pages. That doesn't really happen with B+ trees. So why do we say it's a B+ tree? It's a B tree that stores data entries in the leaves only. If you remember B trees from 61B, this will look very familiar to you. We just add on a couple of twists. So this is an example of what a B+ tree looks like. You have your root node, then you have the index nodes, the level below, still index nodes, 5, 13, 24, 30. And then at the very bottom of the B+ tree, you'll have your leaf nodes. And the leaf nodes are the ones that will actually have things to do with data. There are some invariants that we have to fulfill. Number one, each interior node has to be at least partially full. You can't have an empty node sitting right there. Number two, I want to introduce this term called D. D is going to be something we call the order of the tree. And if you want a simple explanation of what it is, just think of it like this. A B plus tree of order D means that, outside the root at least, each node has to have at least D entries and at most 2D entries. One more advantage of a B plus tree is now the data pages at the bottom might not be stored in logical order on disk. That's all right. We're going to have next and previous pointers that will link the leaf node / data pages together. Okay? So these leaf nodes at the bottom are going to be linked together by like next and previous. And that's good because when you get to the bottom, you can do sort of like a range scan or like you can do just like a walk through the leaf node pages. So when I get to the node indicating 2, 3, I can just, if I want to search for all the values greater than 3, well, I'll get to 2, 3, and now I'll just follow the pointer right, go to the node of 5, 7, 8, follow that pointer, go to the node of 14, 16, et cetera, et cetera. I don't need to go all the way back up to the root and then find the pointer for the next leaf page because I can just follow a chain to get to the end. Right, so a quick sanity check here. What's the value of D? Guys, come on. You guys can talk. Good. Okay, the value of D is 2. So now you might ask, what about the root? And the root is kind of a special case, okay? If anyone here is an oldest child, you know how the youngest kid always gets to do stuff that we never got to do? Okay, like, I'm sure like half the people in this room felt it. Basically, the root is an exception here. It's an exception because otherwise our B plus tree doesn't really work. We're going to let the root not satisfy that occupancy invariant, but everything else will need to follow that invariant of each node having at least D entries and at most 2D entries. The root will just be capped at 2D entries, but it can just have one entry and that's fine. Okay? All right, I said also that these pages might not be in sequential order on disk, and so we're going to have that chain instead, those pointers next and previous. You might ask, well, why is it not in sequential order on disk? And the answer is, these pages are going to be allocated dynamically. As we need more pages, as our tree grows, we will allocate those pages dynamically by, as and when needed. If that doesn't make sense now, it's okay. We're going to go over how insertion works and how splits happen, and then you'll see what I mean. Okay? So let's talk a little bit about B plus trees and their scale. So if D equals 2 and the height is 1, look at how many records you can fit in here. Okay? You have 4 values at most that could fit in the root node. Each of those values will have a pointer to the left and to the right. Now, if you count that, you'll see that there are 5 pointers to leaf nodes. Each of the leaf nodes can hold 4 records. Therefore, your B plus tree of order 2 can hold 20 records if it's height 1. But now look at this. This is only height 3. And now this is amazing. Remember that this is basically a height of a tree is like how many levels you have to traverse through to get to the leaf node. to get to where the data is stored almost, right? Well, height 1 could only store 20 records. Height 3 can store 500. Because it grows in that multiplicative way. Does everyone kind of see that from the diagram? And so this is a very, very powerful concept that enables lookup to be extremely easy for very, very large files, and actually enables this to be something we can use to speed up a lot of different things. In some of your internships sometimes, or in the real world when you're actually working on stuff, some people will say if you add an index to something, it'll make it go faster. What does that actually mean? This is what it means. So in practice, the typical order is something like 1600, and typically you have like a fill factor of like 67%. Okay? So your average fan out is going to be something like 2144. Okay? Now, at typical capacities, you can see how many records you can actually store. And that's amazing. Because the truth is, if you have a B+ tree of an order that's very big, well, the bigger your order is, the more keys you can store in a node. The more keys you can store in a node, the more pointers you can have to child nodes. The more pointers you can have to child nodes, the more data you can store. Okay, and so typically in industry, you don't see B+ trees of order 2. That doesn't make any sense. It's kind of a waste of space, but you will see them be of like order 1,000, 2,000, etc. And that's entirely because you want to take advantage of this property where as your order grows bigger and bigger, it grows by a multiplicative factor, or I guess a exponential factor every time. So is it clear to people how a big order how the bigger the order gets, you get a drastic improvement in the number of records you can store at the root? Okay. All right. So, how do we search a B+ tree? Let's walk through an example. Okay? So let's try to find our key 27. So what do we do in ISAM? We took a look at each node and then we kind of binary searched on it. Right, so we start at the root node and binary search. 27. Well, it's going to be greater than 17. So we go to the node of 24 and 30. It's going to be greater than 24 and less than 30. So we'll follow the pointer that's allocated to the right of 24 to the left of 30. We'll go down to the leaf level, and now we have our node. And we can just search at that leaf level for the value 27. Is this part clear to everyone? Okay, this is really important, so give me a thumbs up if you understand this. Okay, let's move on. So, fetching data in a B+ tree, typically what you'll find is that when you get to the leaf level, that has the keys containing what you need, right? It has like keys and pointers to the record associated with the keys. Now sometimes you will directly have those records stored in the leaf level, but a lot of the time, that can be a little bit inefficient. Why would that be a little bit inefficient? Does anyone know? Anyone? Yes. Yeah, so a way of thinking about it is if I store the records in the leaf level themselves, and I can do that, and we will go over what happens when you do that. That is done by many people. But if I store the records in the leaf level themselves, well, the records are pretty big, right? So that's going to be a little bit, more restrictive on the amount of stuff we can store than if I just had the record, if I just had the key and then a pointer to the record. Right, like, yeah, we would have to pay a little bit extra in that we need one more I/O, because then you get to the bottom, you follow the pointer to disk, and then, you pull that out. But also it means I can store a lot more on a page. Right, so it's that trade-off you have to investigate. Yes? Okay, so a key is typically like, if you think about a schema of a table, let's take the students table. A key might be SID. So it's not always a primary key. A key in a B+ tree is not necessarily always a primary key. I could have a tree built on the student's name. But a key is basically just a column in the table that you can efficiently and easily search with. Really speaking, if you want a concrete definition, I guess just think of it like the key in a B+ tree will be a column in a table, and then you'll use that to search through the B+ tree and then fetch the record associated with, where the value of the field in that record is equal to the, or satisfies the condition that you set on that field. Yes? Trade-offs for having too many indexes, space, right? Can be a little bit costly. So, yeah. Yeah, so if you're looking for 24 exactly, 17, 24, you get to the 24 is greater than 17. So you'll follow the value to the right. 24, 30. So it's going to be, if it's greater than or equal to 24, you go right. It's greater than or equal to, you go to the right, less than, you go to the left. Okay, let's keep moving. Okay, so now let's talk about insertion in a B+ tree. Let's insert 25, and let's just walk through this example together. Okay, so you're going to find the correct leaf. How do you find the correct leaf? You're going to have to, do your walkthrough. Conduct your search, you'll find where to insert it. And now, if there's room in the leaf, you can just add it, right? There's room in the leaf, you can just add the entry. And all is good. Once you add the entry, you're going to want to sort the leaf page by the key. And that's all right. That's not very expensive. You can just, 24, 27, 29, 25, it's very cheap to just sort it because the data page is already in memory. So you can just sort it there and write it back. Okay? But sometimes you'll end up in an example where the leaf node is already full, and so the key won't go, like 8. So what do we do here? We're going to have to learn how to split a node. And what happens to the B+ tree when you split a node? So when you split a leaf node, what you're going to do is, now you'll have a sequence of values. Here you have 2, 3, 5, 7, 8. Okay? You're going to want to make sure you sort those values. Okay? And you're going to redistribute those entries evenly. What does that mean? You're going to take D entries and put them in the left. The order of the tree here is 2, right? D equals 2. You can see that it can store 4 entries in a node, so D equals 2. And you're going to put D entries in the left node, D plus 1 entries in the new node, the right node. Okay, and then you're going to fix your next and your previous pointers. So you can now continue to maintain your sorted order. And you think we're done. You think we're done. But as it turns out, we've missed something here. Can anyone point out what's missing? Right, basically if we keep doing this and we don't actually, do something to have this reflected in the higher levels, the split reflected in the higher levels, I mean, have we actually improved anything from our last attempt at this in ISAM? No, not really. So we need a way to track. We need something, we need a way to track that new node that isn't just following the pointers from the leaf node, right? Because right now this node is an orphan. So we're going to do something to fix that. We're going to copy up the middle key. We just split 2, 3, 5, 7, 8. You take the middle key from that sequence, and there will always be one middle key, right? Because you have 2D plus 1 entries at the time of a split. You're going to take the middle entry, and you're going to copy it up from the leaf to the root node. Okay, now what happens if your parent node is also full? We're going to recursively split the index nodes. How does that work? Once again, we're going to sort these values in the index node, and we're going to take D entries and keep them in the left node, and take the D rightmost entries and move them to the right node. Now, very important, watch what happens here. I said D entries in the left node and D entries in the right. Well, hang on a second. I just said there were 2D plus 1 keys at the time of a split. So what do I do with that middle key? Just keep the leftmost D keys in the left node, the rightmost D keys in the right node. The middle key is going to be pushed up. That 17 is going to be pushed up. It's not going to be copied up. It's going to be pushed up. Okay? This is a very important point. Please note this down. Oh, I'm sorry, PowerPoint, Google Slides does not like how I imported the PowerPoint, so the arrows are a little bit messy. That slide will be fixed before tonight, don't worry about that. But does everyone so far see how splits have worked? Okay, I'm going to go over now why we copied up the leaf node, but we pushed up the index node. This is really important. Basically, what happens is the leaf node stores, what did I say the leaf node had? It had connection to the actual records. It had connection to the data. Right? So I can't just move a leaf node key up, because let's say I moved 5 up. Well, that's a problem, because what does that value at the leaf node actually represent? It represents that there is a record with the matching value of that key. So I need that at my leaf node. If I don't have that at my leaf node, I'm in trouble, because I've essentially just lost a pointer to an actual row. But the index nodes, they're only there for navigation. They're your GPS. They're there to tell you, go to the left, go to the right, go to the left, go to the right. They're just there for direction. And because they're just there for direction, you don't have to worry about losing a value at an index node level. You can just push it up. And that's better because, there's no need for you to store that value 17 in this index node. That's just taking up extra space. No, would be better. Let's, just add a new node that will tell you whether to go right or left. And we'll just make those two old index nodes children of this new root node. So are people clear so far on why you push up versus copy up? Index nodes you push up, leaf nodes you copy up? Okay, give me a thumbs up if you understand it. Okay. Seems like the majority of the class so far, so I will move on. If you have questions, I'll come around in the middle too. Yes? Yeah, so I'm actually going to go over that slide now. Okay, so now we're going to basically here, I just want to take a quick concept check. And let's check the invariance that we had established at the beginning of the lecture. What is an invariant was a question that was asked. It's basically a property that has to be obeyed for this tree. Okay? The key invariance, okay, which basically said greater than or equal to the right, less than to the left. And the occupancy invariant, which says outside of the root node, you have to have at least d entries in every node, and you can't have more than 2 d entries in a node. Those, as we can visually see, are all obeyed here. Yeah, I'm sorry about the weird arrows here. When you import from PowerPoint, sometimes things get a little bit funky in Google Slides. But in case anyone's confused, these should just be chains of arrows linking the nodes together. Bidirectional chains. It's like a doubly linked list. Okay? So the rough algorithm sketch of a B+ tree insert is going to be, you're going to first find the correct leaf. You kind of like do an equality search to find the relevant leaf for that. And then you're going to basically just put the data entry onto that leaf page. And if that has enough space, if that leaf page had enough space for you to put your entry in, you're done. Otherwise, you're going to need to split the leaf node into that leaf node and a new one. And in that leaf node, you will basically keep the left entries, and then in the new leaf node, you'll take the rightmost d plus 1. So d in the left, d plus 1 in the right. Then you're going to copy up that value from the middle, and you're going to move that into the, or you're going to copy that up and insert that into the level above, into the parent. And that step can happen recursively. You might need to split the index node. Okay, so once I've copied up that value from the leaf node, I could get to my index node parent and be like, oh shoot, this is full too. What do I do? Okay, I'll need to split the index node. How do I split the index node? D entries to the left, D entries to the right, push up the middle key. Don't copy, push up. And so you can see here that eventually, if we keep splitting and splitting, we're going to end up hitting the root. As we hit the root, you're going to insert the value in the root if you have to really go all that way, if everything below it was full. When you hit the root, if the root is full also, and the root needs to split, that's when the tree's height increases. So the tree height grows with the root split. So you can probably see why it's useful to have trees of order 1600, right? Because it's going to take a lot to actually fill up one of those root nodes. Because you have to fill up everything below it too in that layer, or in that chain to the bottom. Okay, so one thing I just want to point out, all the paths from the root to the leaves are going to be of equal length, okay? This tree is always going to be balanced. Right? And again, I cannot emphasize this enough, you're not going to have a spindly B+ tree. That doesn't happen. I know in 61B they talked about spindly trees, etc. That doesn't happen here. The algorithm is designed so that your tree will always be balanced. Okay? The occupancy invariant does hold here. All the nodes except for the root are going to be at least half full. You can prove that because anytime a node except for the root is there, well, if you think about it, anytime a node is split, it gets at least D entries, correct? So everything would have, assuming no deletions, everything would have at least D entries up until you get to the root. Is that intuitively kind of clear to folks? Okay. All right, so just went over this, but once again, I'll leave this up here in case people want to copy it down very briefly, because I saw some very frantic writing and then a couple of panicked faces when I moved away. So I will leave this here for a second while folks copy it down. Am I good to move on? Okay, I'll give it like 20 more seconds. All right. Okay, so splitting an inner node, once again, you're going to push the key up to the parent, and you're going to just rearrange your pointers. All right, so as you push the 17 up, now you'll have a pointer to the right, and then you're also going to have a pointer to the left for it. Okay. So there's this nice animation online of B+ trees. Small difference to note here. It's in general a good animation, but sometimes here on the deletion of the leftmost value in that animation, it will update the parent index entry. That actually just incurs unnecessary writes. That's not the way we teach it here. But if you're having trouble with B+ trees and you want an outside resource, this is a pretty good one to kind of help get your head around it. But what will be tested is what I just taught here, what we teach in section. Okay, deletion is the next intuitive question, like what happens during deletion? We're going to largely skip that, okay? In practice, that occupancy invariant, while nice, is often not enforced. Why? Because, I mean, it doesn't really matter, I guess. You're just going to delete the entry and then leave some space. Right? You'll get to the leaf node, you'll delete the entry, and it's pretty expensive to rearrange the tree. You just kind of leave it be. Okay, like if a page becomes completely empty, I guess you can delete it. Now you might say, wait, but if you delete a page in the leaf node, you delete an entire leaf node, doesn't that leave the parent under full in a sense? Yeah, it does. That's all right. Okay, because the truth is, like most engineering efforts, we're really optimizing for efficiency and not for mathematical correctness. The truth is, when you're working on stuff in industry, and your boss asks you what's 3,238 times 5,339, if you say, oh, it's 15 million, that's not the answer, but it's close enough. And if you're trying to guesstimate what the cost is, they'll often just take that. They'll be like, oh, okay, well, yeah, it seems about right. It's in the ballpark. Let's just go with it. Okay, don't tell anyone I told you that, but that's basically what it is. We're just trying to optimize for performance here. The key is the guarantees are still attractive. It's a very efficient way to store data, and that, you know, it's going to grow, like your height will be like a logarithmic factor of the number of records you have. Right? And that's really what's important. So let's talk about an important optimization called bulk loading. Okay, well, let's suppose we want to build an index on a large table from scratch. So you could do what we just did here. You could just call insert repeatedly. But would that be efficient? Probably not. The reason for that is because, well, if you're going to do that, you're going to need to continuously search from the root, and then you're going to have to modify random pages. Okay, so it's like, let's say I had a tree and I want to insert 4. So I'll search for the right page to insert 4. I'll insert 4. Then I want to insert 5. I have to start at the root again. Then I have to go all the way down and insert 5. And then I want to insert 6. Now I have to start at the root again. You know, eventually this just gets to be a little bit annoying. Right? It gets to be very inefficient. So, one of the other problems here is also bad cache efficiency. I'll have to visit and modify random pages. And then also, the leaves are going to be half empty because of what happens on a split. Remember what I said on a split? On a split, you're going to take half to the left, half to the right. Well, that's kind of a problem. Almost as big of a problem as lights going off. I really hope they turn on again. All right. So let's be a little bit smarter about what we do. Let's bulk load a B+ tree in a somewhat intelligent way. We're going to first sort the input records by a key. And we'll learn a good way to sort it on disk very soon, but not for today. For now, just assume we're going to sort it and don't question how. Okay? We're going to fill the leaf pages to some fill factor. We're going to say if at least, let's take the number 3/4 here. Let's, load values into a leaf page until you hit the fill factor. Like if the page is at least 3/4 full. Until the page is at least 3/4 full, keep putting in values. Then, when you're going to insert into a page, just check, is it 3/4 full? No, insert a value. Is it 3/4 full? No, insert a value. Eventually, when that thing is, eventually when the leaf node gets filled up to the fill factor, then you'll allocate a new node, and then, you'll do kind of what you'll almost do what you did on a split in a sense, and that new value will also be in the index node. And let me go over what I mean by that. Okay, so you have 1, 2, 3. Now it's 3/4 full. Okay? Now we're going to need a new leaf node. So because we need a new leaf node, we're also going to need a new index node, because now we need a way to track the two index nodes. So 4 is the first value in the new leaf page. So 4 will also go in the parent. And then I will have, my next values, 5 and 6, and they will be inserted here. Okay? And I can continue 7, 8, 9. The 7 goes up in the index. 10, 11, 12. 10 goes up into the root. 13, 14, 15. 13 will go up in the root. Now, let's say that the root is full, so I'll have 16, 17, 18. I want to insert that, now the root is full. What do I do? Well, I will just obey the same split rule as I have in B+ trees. The only thing unique here is how the leaf nodes are treated. Okay, so the parents will still obey the same split rules. 16 is there, so I'll have 4, 7, 10, 13, 16 in the root node. That's 1 too big. So 10 goes up, 4 and 7 and 13 and 16 are your two, level down index nodes. Okay? All right. What's important to remember here is in the process of bulk loading, once the leaves are filled, to that point, to the fill factor, that's it. You don't touch them again in a sense. Okay? You don't insert anything more in the bulk loading algorithm into those leaves. You might, once you finish building your tree, then of course you might want to insert some stuff in the pages, right? Into any page you want, because then it's just like a normal B+ tree again. But key thing I'm trying to say is, in the process of bulk loading, you just fill up a page to the fill factor, and then you move on to the next one. Right? So you're not going to write anything more to that page. Okay? Another key thing to remember, this subtree is not going to be touched again in general in the process of bulk loading. Okay? If that root node gets full, then the root node will kind of just get reallocated or split the root node overgrows, and it'll just split, and then you'll, push up the middle key in the root node again, et cetera, et cetera. But there, important thing to remember is you're only going to be modifying the pointers on the two new nodes you've created in the root and then the new root node. You're not touching this circled subtree again. Do people kind of see what I'm getting at here? Okay. Thumbs up if bulk loading makes sense to you so far. Okay, give me a sideways if you kind of understand it. Okay, give me a thumbs down if you have absolutely no clue what just happened. Okay, so I see mostly thumbs up, a couple of sideways. I see a couple thumbs down. I'll come around in a bit. Okay? So if we continue the process of bulk loading, remember that subtree, gray it out. We're not going to revisit that for the point of bulk loading. Okay, so we're going to keep continuing on our bulk loading procedure, and eventually we'll finish building our tree. Now it's just like a normal tree. Now we can insert, retrieve, delete, whatever we want. It's just like any other tree. But what's good about this? What's different? Well, number one, I'm utilizing my cache a little bit more efficiently. Okay? This is better than insertion into some random locations. Pages can be essentially, allocated sequentially in a sense. Okay? Other important thing here is that the root nodes are full. Or, sorry, not root nodes. Leaf nodes are much more full. Leaf nodes are much more full than what they would have been with a regular insertion procedure. Because the leaf nodes are much more full than what they would have been in a regular insertion procedure. If I was inserting normally, I'd have 2 values per leaf node. Right? Now I have 3 per leaf node because the fill factor is 3/4. And what that means is I can insert a lot more into the tree when I'm constructing it. So the height stays low. And because the height stays low, because I'm inserting many more values in before a split, because the height stays low, it's more efficient to find things because I have to traverse through fewer index nodes to get to the leaf nodes I need. Is that part clear to people? Okay. Quick aside, definition of height. The definition of height is the number of pointers you have to traverse to get from the root to the leaf. In this case, the height is 2. Okay, please do not say the height is 3. It is not. The height here is 2. Okay? So, these are the benefits. Better cache utilization, better layout of leaf pages. They're more sequential. And I utilize leaf nodes a little bit more and the tree's a little bit shallower. Okay? And here's a summary of bulk loading. If you did the multiple inserts, bad. If you did bulk loading, good. That's to construct a tree from scratch, construct an index from scratch. Yes? No, bulk loading is only for the creation of a tree. Okay? So let's summarize B+ trees a little bit. Okay? ISAM is essentially, it was a static structure. We only modified the leaf pages, and so we need some overflow pages. That wasn't great because we'd get these overflow chains of sort, and so we went to B+ trees. These are a balanced structure. It's dynamic. Okay? They're going to be a lot more efficient and a lot easier to search with than if you just maintained a sorted file. Okay? The high fan out is the biggest plus, the biggest attraction of a B+ tree. Why? Because it means that your depth is very rarely more than 3 or 4 in practice. And so that in turn means, hey, That's great because all of a sudden, finding any value in a B plus tree to get to the page itself, it'll take you only a few IOs. You can count the number of IOs on your finger to get to the page that contains your data. A lot better, you can imagine, than doing binary search in a sorted file that's very big, because you could hit God knows how many pages. Easier way for me to put it, log base 2 of 1024, 10. Log base 100 of 1024, round up, it's 2. You guys see the point, right? That's why B plus trees exist. Okay? Lastly, bulk loading, way faster than repeated inserts for creating a B plus tree in a large data set. I don't have to traverse through the index nodes repeatedly to insert something, and I keep my leaf nodes a lot more full. Better sequential layout of my leaf pages, things are just a lot better. Okay? B plus trees this is one of the most optimized components of a DBMS. It's very, very widely used. This is one of the most useful things that you will learn in this class. It's very, very efficient, very widely used. Okay, like if you didn't take much from this class at the end of the day, but you still know what indexes are and how they work, you still gained a lot. Okay, I have talked a lot, and so let's give it like a 5-minute break or so, and then I'll get into a little bit more of the next lecture, which was refinements and index alternatives. I got a lot of questions when I walked around about a couple of things. Okay? First thing that a lot of people asked about was, can you have multiple B plus trees on different indexes? Right? For example, if I had the table of students, could I have one index on SID and another on major? Yes, of course. And that is actually one of the big advantages. Because I can now, instead of, previously when we only knew about sorted files, what would we do? We'd have to have 2 copies of the file. And we would need to sort both of them. One would need to be sorted on major, one would need to be sorted on SID. Not so much anymore, right? Here, I can just build a B plus tree on each of them. And I'll just have, at the leaf nodes, pointers to the spot in the file where that record exists. Okay? And that's one of the big uses of a B plus tree. Okay. The other questions that I got were mainly centered around, like, when is bulk loading actually used? It's used to create a B plus tree. It's just used to create a B plus tree, and it's much more efficient to create a B plus tree that way. Okay. I'm going to go over a little bit about composite search keys, and then we'll let you guys go. Okay. Sometimes we're going to have a composite search key. And what does that actually mean? It means, like, let's say on this table here, what if I had a search key age salary? So it would be ordered lexicographically by the search key. It would be first sorted on age, and if there's a tie on age, then it's sorted by salary. Okay. So, here's a definition that looks a little bit daunting, but just stay with me for a second. We're going to say that a composite search key on a set of columns matches a query if the query is a conjunction of some number of equality clauses that, set certain values of the certain columns equal to certain values, and there is at most one additional range clause. Okay? And the reason this is called a match is you can then look up and scan in lexicographical order. What that means is you'll basically do a lookup on your equality conjuncts to find the start of your range in the B plus tree, and then you'll continue scanning the contiguous data entries at the leaves that satisfy that range conjunct. That's confusing in the abstract, so let's walk through an example. Let's say we have green for rows that we visit that are going to be in the range, and red for rows that we visit that are not in the range. Okay? And this will become pretty clear quickly. Let's say my query says age is equal to 31 and salary is equal to 400. Okay. So, is that a valid, what do we call it here? Is that a valid composite search key? Is this a valid query, rather? Or is this a match? Yes. You can do that. Age is equal to 31, salary is equal to 400. Now, there's no row that matches that, but that's okay. It's a valid query. Okay? What about age is 55 and salary is greater than 200? Here I'll find the match, age is equal to 55, and the salary for that associated record is going to be 400. Okay, what next? Now I'll go scan the next record. Age is going to be 79, so the row is going to be red. Okay? Because the row is red, I'll stop. That's not a match. And again, this is considered a match. This is good. This allows you to search a range. Okay? What about age is greater than 31 and salary is going to be equal to 400? Okay, here, I'll get to the relevant index node. And now I run into some trouble. Why is that? Because this is not a lexicographic range. Okay. So a lot of people would ask at this point, why is this not a lexicographic range? This is why I wanted to go over it visually. Sorry, I think I said query before, but what I meant was this is a valid lexicographic range, the green checks. Okay? The reason this is not a valid lexicographic range, as simple as you can put, if there's red rows in between the green ones, it's not a valid range. A valid lexicographic range means I will hit all my matches sequentially, and when I hit a record that doesn't have the match, then I stop, and I can be guaranteed that I will find nothing else that would have matched. In essence, once I start scanning, I will hit all my matches, and then when I hit a row that isn't a match, I can stop and say, oh, okay, I've hit everything. Okay, so if that convoluted definition didn't make sense to you, that's okay. It never makes sense to any of us. It's a very nice way for people to formalize and overcomplicate things, okay? If anyone here does research, this is what we often call as, oh dear, I'm gonna get in trouble for this, it's okay. This is what they call as over-mathifying things. When you're trying to submit things to a conference and you write too many LaTeX symbols so that people don't understand it and they say, yeah, that seems to check out because they don't want to admit that they don't get it. That's kind of like that complicated notation, okay? Just remember this, if you're trying to find what a lexicographic range is, you're trying to see whether something specified here is a lexicographic range, you basically just do that search through and you see, hang on a sec, am I going to hit anything that isn't a match in between my matches? That's as simple as I can put it. Everyone give me a thumbs up if you get that. Okay. So, see a lot of thumbs ups, a couple of thumbs sideways. That's good. I think it means most of the class got what I'm saying. Okay? But basically, that's the simplest way to put it. That the fact that I have a red row in the middle of the green rows means it's not a valid lexicographic range. What about age is equal to 31? Yeah, that's fine. Age is greater than 31, that's also fine. Okay? What about salary is equal to 300? No. Why? Because this table is actually sorted on age first and then salary. Because it's sorted by age first and then salary, I have to be respectful of that order if I'm trying to look for if I'm trying to define something as a valid lexicographic range. Here it's not, because it's not sorted by salary. Salary is a tiebreaker. Because salary is a tiebreaker, I'm gonna have to bounce through some useless rows here. Because unless I'm using age in the query, I'm not really utilizing the sorted nature of the table. Okay, and so this would not be a valid lexicographic range. Okay? Those are the components that I use to create the slides. That means, basically, thank you for coming, everyone. Hopefully I will see you all on Monday. Hopefully this lecture made a modicum of sense.